Today we're going to be talking about parametric equations and some calculus having to do with parametric equations. So how do we define the slope of a parametric curve? Remember that a parametric curve is defined in terms of t. So we find dy dt and we divide it by dx dt. Now the second derivative is a little bit more complicated. And what you're doing when you're finding the second derivative, remember, is you're finding the derivative with respect to x of dy dt. I'm sorry, dy dx. I was thinking about how I was going to explain this to you. I apologize. And then if you look at this, if I'm taking the derivative with respect to x of this parametric function, I have to take the derivative with respect to t of dy dx all over dx dt. Because remember what you're trying to do is you're trying to take the derivative with respect to t. So it's essentially a chain rule. So what you have is you have dx dt on the bottom, and then you have the derivative of your derivative on the top. This explained another way. Okay. So to calculate the second derivative, you have to use the chain rule twice. So dx dt, okay, of dy dt equals dx dt over dy dt over dx dt, because that's what this is. So then I have to take the derivative of the top with respect to t and the derivative of the bottom with respect to t. So basically what you have is you have the derivative of your derivative on top and then the derivative of dx dt on the bottom. Hopefully that makes sense. I always struggle with explaining that to my students. Okay, so find dy dx for this curve. So let's find dy dt, and that is going to be 2/3 t. Finding dx dt, well, that's going to be 2. So I have 2/3 t to find dy dx over 2. So that simplifies to 1/3 t. I was questioning myself there on my algebra. Okay, so it's actually really not that bad. For a curve given by this, find the slope and the concavity. So I need to find the derivative, and then I need to find the second derivative. So I find dy dt, and that is going to be negative t to the negative 2. I'm going to find dx dt, and that is 2t. So dy dx is negative t to the negative 2 over 2t, which simplifies to this. Okay, I need to plug in 5, 1, but remember, these are x and y coordinates. So I need to get this in terms of t. So if I'm going to use this equation, this one's a little bit easier, I think. If y equals 1, then t has to equal 1. Now just confirm if I plug in t here, 1 for t here, I get negative 5, and I do. Okay, so I need to now evaluate this at t equals 1, so that ends up being negative 1/2. Now I need to find the second derivative. I have my notation wrong here. Okay, so I take the derivative with respect to t of my first derivative, and I multiply and I divide by dx dt. So the derivative with respect to t of my derivative, remember my derivative was negative 1/2 t to the negative third. The derivative of that is 3/2. Bring down the 3, subtract 1 from your exponent. That's negative 4 there. Okay. So that's what goes on the top. 3/2 t to the negative fourth. On the bottom, dx dt, we have that right here. That's 2t. So that simplifies to 3/4 t to the negative fifth. And this is always going to be positive, so we are concave up. Okay, a prolate cycloid. And so that you get an idea of what the graph looks like, it might be fun if you guys graph this in your calculator in parametric mode so that you can kind of see what it looks like. Crosses itself at the point 6 pi 6. Find the equations of both tangent lines. Okay. Ooh, both tangent lines. Okay, so that's kind of giving me a hint that I'm going to have two answers. I just caught that. Okay, so I find dy dt. Finding dy dt, derivative of 6 is 0, derivative of 3 pi cosine t is that. Derivative with respect to x is 6 plus 3 pi cosine t. So my dy dx is equal to negative 3 pi sine t over 6 plus 3 pi cosine t. Now, I need to evaluate this at 6 pi 6, but remember this is an x and this is a y. So I need to get this in terms of t. I am going to use the y coordinate again. If I use the x coordinate, it's a little bit more complicated because I have that t in there and that t in there. So if I set my y coordinate equal to 6, subtract 6, when does cosine equal 0? Cosine equals 0 when t equals plus or minus, I don't know why I have a square root in there. What am I doing? Pi over 2. So I need to evaluate this at pi over 2. When I plug in pi over 2, kind of fun, on the top I get the sine of pi over 2 is 1. So I get a negative 3 pi. I was questioning myself. I plug in pi over 2 on the bottom. That goes to 0, so I have a 6. So my slope is negative pi over 2. So one of my equations is y minus y1 is equal to m times x minus x1. Now if I evaluate dy dx, which is this quantity, at t equals negative pi over 2, I plug in negative pi over 2 sine is negative, so that turns into a positive 3 pi. Negative, that's 0, so I get a 6. So my slope is a positive pi over 2. I think it's kind of fun that the slope is the opposite of at the t. I don't know. I just found that kind of fun. So x minus 6 is equal to pi over 2, x minus 6 pi. Okay. So writing equations of tangent lines. Length of a parametric curve. So I have this on here and I'm kind of mad at myself because technically reviewing what length of a regular curve is change in y over change in x. Okay, but this is what I have here is not a parametric curve, so I kind of don't like this picture. The arc length of a parametric curve is very similar to this. Okay, so the arc length is from one t to another t, the square root, change in x. Well, that's a really fancy way of saying dx dt, change in y. That's a fancy way of saying dy dt, and we're going to integrate that with respect to t. And you're going to need your calculators for these. The book does some stuff where they don't let you, they simplify and they don't use a calculator. I'll let you guys use a calculator. In general, this would be on a calculator section. Okay, so we have this curve. So I need to find dx dt. So that is 4t minus 1/2 t to the negative 1/2. I find dy dt, and that is derivative of tangent the secant squared of t. So now my length is from 0 to 1.5, the square root of dx dt squared plus dy dt squared with respect to t. Now what I might do is in regular function mode, I might put this function in y1. I might put this function in y2, just so that it's a little bit easier to write that, to type that into your calculator. I believe that's what I did last night when I was double checking my notes on these. Okay, but you have to do that in the regular function mode. If you try and do it in the parametric mode, I think it might blow up your calculator. I remember that, I think I remember that from years past, that it just takes a really long time. Okay, so particle motion defined parametrically. This is what you're really going to find on the AP, okay, is speed. So speed, remember, is the magnitude of the distance. So that's why it's magnitude of distance. And the distance traveled over a certain amount of time is given by that expression. So find the path of a particle is represented by those equations where t is the time in seconds. Find the distance of the traveled by the particle in 3 seconds. So distance traveled is an integral. So I have here the length of my curve from 0 to 3 of the square root, all in terms of t, of dx dt squared plus dy dt squared. Dx dt, in this case, is 2. Dy dt is 1/2 4t plus 3 to the negative 1/2 times by 4. If you can do some simplifying, it might help you out. So again, what I did, and I remember doing this one last night, I put that in y1, I put that in y2 in regular function mode. And then I went back to my home screen and I just typed in the integral from 0 to 3 of y1 squared plus y2 squared. It just makes your life a lot easier. Okay? Okay, so that is our parametric equations and calculus. I hope you enjoyed the video. So this is a little supplement at the end of the video. I realized I forgot to give you guys the answers to these on the actual video. I was so excited because this is the last video I have to record for the 2020-2021 school year. So I was a little excited and I forgot that I needed to get you guys the answer, and my pen tablet isn't working, so this is a little bit longer than I wanted it to be. Okay. Well, so the answer for this first one should have been 15.413, and then the answer for this one should have been 6.387. Okay, so those are your answers. I realized that I did that after, so you get an extra supplemental minute. Good times.